Right now, as you sit there, you are made of dead stars. Not poetically, not as a metaphor, literally. The iron in your blood was forged inside a star that exploded before our sun even existed. The calcium holding your skeleton together was cooked up in a stellar furnace billions of years ago. The oxygen you just breathed in, same thing. Every single atom in your body, heavier than helium, has a story that runs through the interior of at least one dying star. And here's the part that honestly still gets me every single time I think about it. We actually know how that happened. We know what the universe looked like a tiny fraction of a second after it began. We can trace the exact chain of events from that first impossible moment all the way to you, sitting here, watching this. But there are also things we genuinely cannot explain yet. What happened before the Big Bang? What is dark matter, the invisible stuff that makes up most of the universe? Why is the universe speeding up when gravity should be slowing it down? And is there even such a thing as a before? Stick around, because by the end of this, you will never look at your own hand the same way again. This is the full story of the universe, from the very first moment anything existed through the birth of stars, galaxies, planets, and life, all the way to what happens billions and trillions of years from now when the last stars burn out and everything goes dark forever. I want to be honest with you about something before we start. When I first really went deep on this material, reading papers, working through lecture series, trying to understand not just the facts but the actual physics behind them, I hit a wall. A big one. I remember sitting at my desk one night trying to understand inflation, genuinely struggling, and thinking, I am probably not qualified to explain this to anyone. But then I realized something. The fact that it was hard for me to understand is exactly why it needs to be explained by someone who had to work for it, not someone who grew up with this knowledge, someone who came to it from the outside and had to find the door in. That is what this is. The whole story, told as clearly and as honestly as I know how. Let us go. Here is the first problem with explaining the Big Bang. The moment you try to describe what happened, language starts failing you. Because the question everyone wants to ask, what was there before the Big Bang, might not have a meaningful answer. Here is why. Time, as we understand it, did not exist before the Big Bang. Space did not exist. There was no before. Asking what came before the Big Bang is a little like asking what is south of the South Pole. The question sounds reasonable, it is grammatically fine, but it is pointing at something that simply does not exist. About 13.8 billion years ago, everything that now exists, every galaxy, every star, every atom, every particle of light, was compressed into a space so small it makes a proton look enormous, and then it expanded. Now, I want to give you what I think is the most important visual in this entire video, because most people picture the Big Bang completely wrong. Picture a balloon. Take a marker and draw 100 dots all over its surface, scattered everywhere. Then start blowing it up. Watch carefully what happens to those dots. Every single one of them moves away from every other one at the same time, not from some central point, from each other. A dot near the top is not moving toward the center of the balloon and then out again. It is moving away from every other dot because the surface itself is expanding. No dot is the center. No dot is where the expansion started. The expansion is happening everywhere simultaneously, in the surface itself. That is how the universe works, except instead of a two-dimensional balloon surface, it is three-dimensional space. Space is not expanding into some pre-existing emptiness. Space itself is getting bigger. There is no edge, there is no center. Everything is moving away from everything else because the fabric of reality is stretching in every direction at once. This is not easy to picture. Honestly, even physicists who spend their careers working with this material find it counterintuitive. If it feels strange, that is not a failure of your imagination. That is just what reality is actually like at this scale. The technical name for that initial state is the singularity, and here's the honest truth. The math breaks down when we try to describe it. Our best theory of gravity, Einstein's general relativity, produces nonsense numbers, actual infinities, when you plug in the conditions of the singularity. This is not a failure of the scientists who developed the theory. It is a signal that the theory is incomplete, that there is a deeper theory waiting to be discovered, one that can handle conditions that extreme. We do not know what that theory is yet, and nobody should pretend otherwise. Keep this question in your head as we move forward. In the very first second of the universe's existence, something happened that almost ended everything before it started. A single tiny asymmetry in the laws of physics was the difference between a universe full of stuff and a universe that destroyed itself instantly. We will get to that shortly. In the first tiny fraction of a second, timescales so small they have no real name in everyday language, the universe went through something called inflation. This is not the same inflation as rising prices. This is something far more dramatic. The universe doubled in size, then doubled again, then again and again and again in a cascade of exponential expansion that happened so fast the word fast does not even approach it. By the time inflation ended, and we are talking about a process that completed before the universe was even a fraction of a second old, the universe had expanded by a factor of at least 10 to the power of 26. Let me try to give that number some weight. If you took a single hydrogen atom and expanded it by that factor, the resulting object would be larger than the entire observable universe is today. That is how much the universe grew in that first fraction of a second. And this matters enormously for everything that came after. Inflation solves problems that had cosmologists completely stumped. Problem 1, when we look at the cosmic microwave background, which is a kind of photograph of the early universe that we can still detect today, the temperature is almost perfectly identical in every direction we look. We are talking about regions on opposite sides of the sky that, if the universe had just been expanding normally since the very beginning, should never have been able to communicate with each other. Light would not have had enough time to travel between them. So how did they end up at the exact same temperature? Inflation solves this. Before inflation happened, the entire region that would eventually become our observable universe was tiny enough that everything could mix, communicate, and equalize. Then inflation stretched that small uniform region to cosmic scales. The uniformity was preserved in the stretching. Problem 2, why does the universe appear spatially flat? General relativity says the large-scale geometry of the universe can take different shapes, curved like the surface of a ball, curved the other way like a saddle, or flat like an infinite sheet. Precise measurements tell us the universe is remarkably flat. Inflation explains this the same way a balloon explains it. Blow up any curved surface enough, and any small patch of it looks flat. The surface of the Earth looks flat to someone standing on it. Inflate the universe by an enormous factor, and any initial curvature gets smoothed out to undetectability. But here's the part that, honestly, I had to sit with for a while before it really landed. Inflation also explains where all the structure in the universe came from. Quantum mechanics, the theory that governs the behavior of matter at the smallest scales, has a built-in feature. You cannot have perfectly empty space. The vacuum is not truly empty. There are constant, tiny, random fluctuations in energy density happening at all scales all the time. These are called quantum fluctuations, and they are as fundamental to reality as anything else in physics. During inflation, those tiny fluctuations got stretched. A region that was microscopically larger in density became cosmically larger in density. A region that was microscopically smaller became cosmically smaller. After inflation, the universe was not perfectly uniform. It had tiny variations in density, imprinted by those quantum fluctuations and blown up to cosmic scales. Those variations, amplified over hundreds of millions of years by gravity, became the seeds of every galaxy, every star, every planet, every living thing that has ever existed. You exist because of quantum noise from the first fraction of a second of the universe. The randomness built into the fundamental laws of physics is why there are galaxies. That's not a poetic way of putting it. That's literally what happened. So inflation set up the structure of the universe, but then came the moment that almost destroyed everything before anything could form. Because when matter first appeared, it came with its exact mirror image, and those two things were designed to annihilate each other completely. The fact that anything survived at all is one of the deepest mysteries in physics. Next. When matter first formed in the hot, dense early universe, it formed alongside antimatter. For every particle of matter, every proton, every electron, a corresponding antiparticle was created. An antiproton, a positron. mirror images with opposite charges but identical mass. And when matter and antimatter meet, they annihilate each other. Both particles are converted entirely into energy. Nothing physical is left, just light. So, if the early universe started with perfectly equal amounts of matter and antimatter, which is what you would expect from symmetry, from the idea that the laws of physics should treat both the same, then everything should have annihilated everything. The universe should have ended up as just a sea of energy with no structure at all. No atoms, no stars, no planets, no nothing. But here you are, which means the universe did not start with perfectly equal amounts. Somewhere in the laws of physics, there is an asymmetry. For every 1 billion antiparticles, there were 1,000,000,001 particles of matter, one extra particle of matter for every billion pairs. When the annihilation was done, when every antiparticle had found a partner and they had destroyed each other, those leftover 1 in a billion particles had nothing to annihilate with. They survived. And those survivors, that thin, impossible residue of matter that survived the most complete destruction in cosmic history, became everything. Every atom in every star in every galaxy in the observable universe. We call this the matter-antimatter asymmetry, or in physics language, baryogenesis, and we do not fully understand why it exists. We know it happened. We have partial explanations. There are certain types of particle interactions that treat matter and antimatter slightly differently, a phenomenon called CP violation. But the amount of CP violation we have measured in particle physics experiments is not nearly enough to account for the degree of asymmetry we see in the universe. There is something missing from the picture. The reason you are alive right now, instead of the universe being an empty sea of radiation, is a mystery we have not completely solved. I think about that sometimes when everything feels ordinary. It is not. None of this was guaranteed. The matter that survived then had to go through a very specific set of nuclear reactions that lasted about 3 minutes, only 3 minutes in the entire history of the universe, that permanently determined the chemical composition of everything that has ever existed or will ever exist. And the fact that we can calculate the predictions of those 3 minutes and check them against observations 13.8 billion years later is one of the most extraordinary achievements in science. Here is how it worked. After the matter-antimatter annihilation, the universe was a hot, dense soup of protons, neutrons, electrons, and photons. Insanely hot. We're talking hundreds of millions of degrees. At those temperatures, protons and neutrons had enough energy to fuse together. Starting from about 1 second after the Big Bang, nuclear fusion began happening everywhere simultaneously throughout the universe. Protons and neutrons slammed into each other with enough force to stick. They formed deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Deuterium then fused with more particles to form helium. Small amounts of lithium got made, traces of beryllium. But then, at around the 3-minute mark, the universe had expanded and cooled enough that the particles no longer had enough energy to overcome the repulsion between nuclei. The fusion stopped. The window closed. In 3 minutes, the cosmic kitchen had done its work, and the result was a very specific recipe. Roughly 75% hydrogen and 25% helium by mass, with trace amounts of lithium. Almost nothing else. This is called Big Bang nucleosynthesis, and it is one of the most powerful tests of the Big Bang model. Because that recipe, 3/4 hydrogen, 1/4 helium, is an extremely specific prediction. And when astronomers look at the oldest, most chemically pristine gas in the universe, ancient gas clouds that have not been enriched by the heavy elements that later generations of stars would produce, they find almost exactly that ratio. The theory predicted a number, the observations confirmed it. That is not a coincidence. That is evidence. Everything heavier than lithium, carbon, oxygen, iron, gold, uranium, would have to wait. It would have to be made later, inside stars, in a process that took billions of years. The universe, in its first 3 minutes, could only build the lightest elements. The rest of the periodic table had to be assembled by stellar furnaces over the subsequent billions of years of cosmic history. You are made mostly of hydrogen and helium, which is what the Big Bang made directly. Everything else in you is a product of later stellar evolution. You are a collaboration between the Big Bang and several generations of stars. After those first 3 minutes, the universe went quiet. For roughly 380,000 years, it was a hot, glowing fog that light could not escape from. Then something happened that released a flash of light so old and so far traveled that it is still reaching us today. And the story of how that flash was accidentally discovered involves pigeons, which is not what you would expect. For the first 380,000 years after the Big Bang, the universe was filled with plasma, a hot soup of free electrons and atomic nuclei. Photons, particles of light, were constantly bouncing off those free electrons. They could not travel more than a short distance before hitting another electron and getting scattered. The universe was completely opaque, like trying to see through a dense cloud from the inside. Then, as the universe expanded and cooled, it reached a temperature of around 3,000 degrees. At this temperature, called the recombination epoch, even though it is a slightly misleading name since electrons and nuclei had never actually been combined before, electrons and nuclei could finally come together to form neutral atoms, mostly hydrogen, some helium. The moment neutral atoms formed, the free electrons that had been blocking light disappeared. There was nothing left for photons to bounce off. The fog cleared instantly, cosmically speaking, and all the light that had been trapped in the plasma was released simultaneously, streaming out in all directions across the universe. That light has been traveling ever since, for 13.8 billion years. The universe has expanded enormously in that time, and the expansion stretched the wavelength of those ancient photons, shifted them from visible light down through infrared all the way into microwave radiation. What we detect today as the cosmic microwave background, the CMB, is that ancient light, now cooled and stretched by billions of years of cosmic expansion. Here is the story of how it was discovered, and I love it because it involves a complete accident and some very inconvenient birds. In 1964, two radio astronomers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna at Bell Labs in Holmdel, New Jersey. They were trying to make precise radio astronomy measurements, but they kept picking up a faint, persistent background noise that they could not explain. The noise was coming equally from every direction in the sky, regardless of where they pointed the antenna. It was slightly stronger than it should have been based on the known sources of radio interference. They were baffled. They checked all their equipment, they recalibrated everything, they found two pigeons nesting inside the antenna and removed them. The pigeons came back. They removed the pigeons again, more permanently this time, and carefully cleaned what the birds had left behind. The official scientific account uses the phrase white dielectric material, which is a charming euphemism. Still, the noise was there. Eventually, through a colleague, Penzias and Wilson learned that a group at Princeton had been specifically predicting the existence of a cosmic background radiation, the afterglow of the Big Bang, and had been preparing to search for it. Penzias and Wilson had stumbled onto the most cosmologically significant discovery of the century while trying to figure out what was wrong with their antenna. They won the Nobel Prize in Physics in 1978. The CMB is almost perfectly uniform, the same temperature in every direction to about 1 part in 100,000. But those tiny variations, those 1 in 100,000 fluctuations, are enormously important. They represent slightly denser and slightly less dense regions in the early universe, and those slight differences in density, amplified over hundreds of millions of years by gravity, became the seeds for all the structure we see today. Galaxies, galaxy clusters, the entire cosmic web. The CMB is the oldest light we can detect. It is a photograph of the universe when it was 380,000 years old, and it contains, encoded in its tiny temperature variations, essentially the entire future history of cosmic structure. Scientists have mapped it in extraordinary detail using satellite missions, And from those maps, they can extract the age of the universe, its composition, its geometry, and much more. It is the most information-rich image ever taken, and we found it because of pigeon droppings. After the CMB was released, the universe went completely dark again. No stars yet, no galaxies, just hydrogen and helium gas cooling slowly in total darkness for hundreds of millions of years. And then, for the first time in cosmic history, light came back on. But the first stars that turned on were so different from our sun that comparing them is almost misleading. What they were like and what they did to the universe is something most people have never heard. After recombination, after the CMB flash, the universe entered what cosmologists genuinely call the Dark Ages. Not metaphorically, literally dark. There were no stars anywhere, no sources of light, just hydrogen and helium gas, gradually cooling as the universe expanded, drifting in total darkness. But gravity was working, quietly, without any light to reveal it, pulling matter together in the slightly denser regions that had been seeded by those ancient quantum fluctuations. Gas clouds grew, collapsed inward. Over tens of millions of years, the density and temperature inside some of these clouds reached a critical point. Nuclear fusion ignited. The first stars turned on. This moment, the end of the Dark Ages, the moment the universe first had light again, is sometimes called cosmic dawn, and it is one of the things the James Webb Space Telescope was specifically built to study, because detecting light from those first stars and galaxies requires a telescope powerful enough to see objects that are 13 billion light-years away and redshifted into the infrared. But here is what made those first stars so extraordinary and so strange compared to anything we see today. The first generation of stars formed from gas that was purely hydrogen and helium, the only elements that existed at the time. And this matters for a reason that is not obvious at first. Heavier elements, the ones that would have to be made inside stars, actually play an important role in the process of star formation. When a gas cloud collapses, it heats up as it compresses, and the temperature can rise high enough to halt the collapse. Heavier elements help the gas radiate away that heat more efficiently, allowing the collapse to continue. Without them, the gas stays hotter and collapses differently. The result is that the very first generation of stars, called population 3 stars by astronomers, probably formed in a fundamentally different way from stars today. They were likely far more massive. Models suggest some of them could be hundreds of times the mass of our sun. Some extreme estimates suggest the very first stars could have been 1,000 solar masses or more. These were objects unlike anything that exists in the universe today. And they were short-lived. The more massive a star is, the faster it burns through its fuel. A star 1,000 times more massive than the sun might live only a few million years, compared to the sun's expected 10 billion-year lifespan. They burned brilliantly and died spectacularly in enormous explosions that scattered their material across space. Those deaths were enormously important. Every heavy element those stars had built, carbon, oxygen, neon, silicon, iron, was blasted out into the surrounding gas. The next generation of stars that formed from that enriched material was different, slightly less extreme, slightly more like what we see today. Each generation made the cosmic environment a little more chemically complex. The Sun is what astronomers call a population 1 star, a third-generation star, formed from gas already enriched by 2 previous cycles of stellar birth and death. The atoms in your body have been through several stars before ending up in you. So stars live, make heavy elements, die, and scatter those elements into space. The next generation forms from richer material. Over billions of years, the universe becomes more chemically complex. But here is what I want you to think about heading into the next section. The very heaviest elements, gold, uranium, iodine, platinum, were not made in ordinary stellar explosions. They were made somewhere else entirely, in an event so extreme and so rare that we only confirmed it was real in 2017. And when we caught it happening, we could watch gold being forged in real time. Nuclear fusion in stars can build elements up to iron in the periodic table. At iron, the process stops releasing energy. Fusing iron actually requires energy rather than producing it. So once a massive star builds up an iron core, fusion stops. The core collapses under its own gravity, and a supernova explosion blasts the outer layers of the star into space. Supernovae are violent enough to create elements a bit heavier than iron, but the conditions are not extreme enough for the very heaviest elements. For those, gold, platinum, uranium, iodine, cesium, dozens of others, you need something more extreme. Something involving conditions so dense and so energetic that they go beyond what any ordinary stellar explosion can produce. For decades, the leading theory was neutron star mergers. Neutron stars are the remnants left behind when certain massive stars collapse, city-sized objects with the mass of the sun packed into a sphere roughly 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. When two of these objects spiral together and collide, the conditions are unlike anything else in the universe, densities and temperatures that dwarf what happens inside a supernova. The theory said that in those extreme conditions, the rapid neutron capture process could build atoms from iron all the way up to uranium and beyond, assembling the heaviest elements in the periodic table in seconds. But for a long time, we had never actually witnessed a neutron star merger. It was a theory without direct observational confirmation. Then, on August 17, 2017, everything changed. The gravitational wave detectors at LIGO in the United States and Virgo in Italy picked up a signal, not from two black holes colliding, which is what LIGO had been detecting previously. This was different. This signal had a different shape, a different duration, about 100 seconds of increasingly rapid gravitational wave emission, the sound of two neutron stars spiraling closer and closer to each other and finally merging. Within seconds of the merger, gamma-ray satellites detected a burst of high-energy radiation from the same direction in the sky. Then, within hours, optical and infrared telescopes around the world swung toward the location, a galaxy called NGC 4993, about 130 million light-years away. What they saw was a kilonova, a brilliant explosion glowing with a characteristic blue and then red light that matched theoretical predictions for the spectral signatures of heavy elements being synthesized in real time. Astronomers watched the light evolve over days, and its spectrum matched what you would expect if enormous quantities of heavy elements were being created and ejected into space. The estimates were extraordinary. That single neutron star merger may have produced gold with a mass of several times Earth's entire mass, scattered into space, eventually to be incorporated into future gas clouds, future solar systems, future planets. Every gold atom on Earth, every gold ring, every gold coin, every gold contact in every electronic device came from an event like that one, an event where two dead stars, the collapsed remnants of two supernovae, spiraled together over billions of years and collided in a fraction of a second. The iodine in your thyroid gland, which your body needs to produce hormones that regulate your metabolism, the platinum in catalytic converters, the uranium in nuclear fuel, all of it forged in the most violent collisions the universe produces. I genuinely had to take a break after I first fully understood this, not because it is impressive trivia, because it means the chemistry that makes life possible did not come easily or cheaply. The universe had to go through specific, rare, violent events in specific sequences over billions of years just to produce the atoms you are made of. You are not casually assembled. You are the product of a very long, very expensive cosmic process. Stars make elements. Neutron star collisions make the heaviest ones. Over billions of years, the universe assembles galaxies containing hundreds of billions of stars, each with their own planetary systems. But at the centers of almost all of these large galaxies sits something that we have only recently managed to see directly. And what it looks like when you finally see it is one of the most surreal things in science. Coming up, the Milky Way, our galaxy. contains somewhere between 200 and 400 billion stars spread across a disk about 100,000 light-years across. Our solar system sits roughly 26,000 light-years from the center, about two-thirds of the way out from the middle. The galaxy is so enormous that even traveling at the speed of light, which nothing with mass can actually do, it would take 100,000 years to cross it from one side to the other. At the center of the Milky Way, buried behind enormous clouds of gas and dust that block visible light entirely, sits a supermassive black hole. We call it Sagittarius A star, written as SGR A star in scientific notation. It has a mass of about 4 million times the mass of our Sun, 4 million suns worth of mass compressed into a region smaller than our solar system. We know it is there because of a decades-long observational campaign. Astronomers have been tracking the motions of individual stars near the galactic center using infrared telescopes that can see through the obscuring dust. These stars are doing something remarkable. They are orbiting at extraordinary speeds around a point where nothing visible exists. Some of them complete one full orbit in just a few years, while our solar system takes 225 million years to go around the galaxy once. The orbital mechanics of those stars match exactly what you would expect if there were a 4 million solar mass object at the center. Then, in 2022, the Event Horizon Telescope collaboration did something extraordinary. The Event Horizon Telescope is not a single instrument. It is a network of radio telescopes spread across the globe in Hawaii, Chile, Spain, the South Pole, and other locations that are synchronized together using atomic clocks to effectively function as a single telescope the size of the entire Earth. The resolving power this creates is staggering. Using this instrument, astronomers produced the first direct image of Sagittarius A star, not an artist's rendering, not a simulation, an actual image made from real light captured by real telescopes, processed into a picture. You can see the black hole's shadow, a dark region at the center, surrounded by a glowing ring of hot gas being heated by the immense gravitational field. The image matches the predictions of general relativity with striking accuracy. We can now see the black hole at the center of our own galaxy. That was not possible even 20 years ago. But supermassive black holes raise a puzzle that cosmologists are actively working on. Every large galaxy we have studied appears to have one. Their masses range from millions to billions of solar masses, and the mass of the central black hole seems to be correlated with properties of the surrounding galaxy, like the total mass of the central stellar bulge, in ways that suggest the black hole and the galaxy co-evolved, each influencing the growth of the other. How do you get from a stellar mass black hole, a few dozen solar masses, the kind that forms when a massive star collapses, to billions of solar masses? That is many orders of magnitude of growth. Current models involve seed black holes growing by accreting gas and dust over billions of years, combined with mergers between black holes when galaxies merge. But the James Webb Space Telescope has already found evidence of surprisingly massive black holes in very early galaxies, galaxies so young that the universe had not had nearly enough time, by current models, for those black holes to grow that large. We do not yet have a complete explanation. The universe assembled these objects faster than we expected. The universe spent its first several billion years building galaxies, seeding them with supermassive black holes, enriching the cosmos with heavier and heavier elements. And then, about 4.6 billion years ago, in a completely ordinary part of a completely ordinary galaxy, a completely ordinary gas cloud collapsed, and the sequence of events that followed, involving an accidental collision, a planet covered in toxic atmosphere, microbes that poisoned their own world, a rock from space, and a lot of small mammals, eventually led to you. But it almost did not happen. Multiple times. About 4.6 billion years ago, a cloud of gas and dust in one of the Milky Way's spiral arms started collapsing. We do not know exactly what triggered it. Possibly a nearby supernova sent a pressure wave through the region and started the process. However it started, gravity did the rest. As the cloud collapsed, it spun faster, the same reason a figure skater pulls their arms in to spin faster. Conservation of angular momentum. A disk of rotating material formed with the bulk of the mass piling up at the center. The center heated up as material fell inward, temperature and pressure building. Eventually, the conditions at the core reached the threshold for nuclear fusion. Our sun ignited. The remaining material in the disk began aggregating. Tiny particles stuck together by electrostatic forces. Pebbles clumped into rocks. Rocks became planetesimals, objects kilometers across. Planetesimals crashed into each other, merging or shattering. Gravity accelerated the process, pulling larger objects together into larger and larger bodies. Closer to the sun, where it was too hot for ice or volatile materials to survive, the building blocks were rock and metal. 4 rocky planets formed: Mercury, Venus, Earth, Mars. Farther out, where ices could exist and there was far more material, larger bodies accumulated. Jupiter and Saturn grew rapidly, becoming so massive that their gravity could capture hydrogen and helium directly from the surrounding disk. They became gas giants. Uranus and Neptune formed further out as ice giants, smaller than Jupiter and Saturn, but still enormous by inner solar system standards. The Moon most likely came from a catastrophe. Current models suggest that roughly 4.5 billion years ago, when the Earth was still young and partially molten, a Mars-sized object, sometimes called Theia, struck the Earth at an angle. The impact was not a direct hit, but a glancing blow that was still enormously energetic. It melted the outer layer of the Earth and blasted an enormous amount of material into orbit around our planet. That orbiting debris gradually coalesced into the Moon. Evidence for this comes from the composition of moon rocks returned by Apollo astronauts. The Moon's composition closely matches Earth's mantle in ways that are very hard to explain by any other mechanism. The giant impact hypothesis is not proven beyond all doubt, but it is the best explanation we have for why the Moon exists and why it has the composition it does. Life appeared somewhere around 3.8 to 4 billion years ago. We genuinely do not know exactly how. The origin of life, the gap between chemistry and biology, between interesting molecules and something that can self-replicate and evolve, is one of the most fascinating and most contested areas in all of science. We know the building blocks can form naturally. Amino acids, the components of proteins, have been found in meteorites. Nucleotides, the building blocks of RNA and DNA, can form in simulated early Earth chemistry experiments. But knowing that the ingredients exist is not the same as knowing how they assembled themselves into the first self-replicating system. For the first roughly 2 billion years, all life on Earth was microbial, single-celled, invisible. But these invisible organisms transformed the planet in ways that changed its entire chemical character. About 2.4 billion years ago, cyanobacteria started producing oxygen as a byproduct of using sunlight for energy. This was, from the perspective of most life on Earth at the time, an ecological disaster. Oxygen is reactive. It is toxic to organisms that have not evolved defenses against it. The Great Oxidation Event, the point at which free oxygen began accumulating in the atmosphere, probably caused the first mass extinction in Earth's history. But it also opened an entirely new evolutionary pathway. Organisms that evolved to use oxygen in metabolism could extract dramatically more energy from food than anaerobic organisms. Over hundreds of millions of years, this energy advantage enabled the evolution of complex multicellular life. The Cambrian explosion, about 540 million years ago, saw a rapid diversification of complex animal body plans, eyes, limbs, shells, internal structures in a geologically brief period. Fish appeared, plants colonized the land, insects evolved, amphibians made the transition from water to land, Reptiles diverged from amphibians. The dinosaurs arose around 230 million years ago and dominated terrestrial ecosystems for 165 million years. And then, 66 million years ago, an asteroid roughly 10 kilometers across struck the Shalin Sea off the coast of what is now Mexico's Yucatan Peninsula. The energy released by the impact was staggering. Billions of tons of material were launched into the stratosphere, blocking sunlight globally for years. Wildfires spread across continents. Food chains collapsed. About 75% of all species on Earth went extinct, including every non-avian dinosaur. The small, mostly nocturnal mammals that had been living in the shadow of the dinosaurs found themselves in a world where the dominant animals were suddenly gone. They diversified explosively, filled every available niche. About 6 to 7 million years ago, a particular mammal lineage diverged. One branch led to chimpanzees. The other eventually led, through several intermediate species, to us. About 300,000 years ago, anatomically modern humans appeared in Africa. And somewhere between 50,000 and 70,000 years ago, something shifted. The emergence of complex symbolic thought, language, the ability to share and accumulate knowledge across generations. About 12,000 years ago, agriculture, then settled cities, writing, trade networks, mathematics, science, the telescope, the atomic theory, the discovery of DNA, the particle accelerator, the detection of gravitational waves. From a quantum fluctuation 13.8 billion years ago to you watching this video. That is the chain. That is the past. But the story of the universe is not over. And what happens next, over the next trillions upon trillions of years, is something most people have never really thought about, because the future of the universe is genuinely strange, and it ends in a way that is both beautiful and profoundly quiet. The universe right now is in what cosmologists call the stelliferous era, the era of stars. Galaxies are actively forming new stars. The universe is full of light, full of energy from nuclear fusion, full of activity on every scale. It feels like this is just how things are and how they will always be. It is not. Star formation requires gas, and that gas is being used up. Stars form, burn their fuel, and die. Some of their material gets recycled back into space, where it can eventually form new stars. But some gets locked away permanently, in the cooling remnants of dead stars, in black holes, in forms that will never participate in star formation again. The raw material is slowly being depleted. The rate of star formation in the universe peaked about 10 billion years ago. It has been declining steadily ever since. The universe is gradually becoming a dimmer, quieter place. In roughly 100 trillion years, that is a 1 followed by 14 zeros, about 7,000 times the current age of the universe, the last ordinary stars will burn out. The stelliferous era will end. What follows is called the degenerate era. The universe will be populated mainly by stellar remnants. White dwarfs, the burned-out carbon-oxygen cores of sun-like stars, will cool slowly, incredibly slowly, over timescales that dwarf the current age of the universe. They will fade from white to yellow to orange to red, dropping in temperature over incomprehensible timescales. Eventually, they become what we call black dwarfs, cold, dark, inert objects in space. No energy output, no light, just slowly cooling lumps of crystallized carbon floating in the dark. Here is something that puts the timescale in perspective. Not a single black dwarf exists yet. The universe is not old enough. The cooling process takes longer than the universe has currently existed. Every white dwarf that has ever formed is still glowing, still detectable. The era of black dwarfs lies trillions of years in our future. Some theories predict that protons, the particles that make up the cores of atoms, will eventually decay. The standard model of particle physics treats protons as stable, but some extensions of the standard model, Particularly theories that attempt to unify the strong and electro-weak forces predict that protons should have an incredibly long but finite half-life, perhaps 10 to the power of 34 years, perhaps longer. If protons decay, then all the matter locked up in white dwarfs and neutron stars will gradually dissolve, particle by particle, over an incomprehensible expanse of time. The matter of the universe itself will evaporate. Experiments are running right now in underground laboratories shielded from cosmic rays, watching enormous tanks of water for the rare event of a proton decaying. So far, nothing. But the experiments push the limits of the possible half-life further and further with each passing year of data collection. Then there are the black holes. Even after the stars burn out and the protons potentially decay, black holes persist. They are extraordinarily stable objects. Nothing that falls past the event horizon ever emerges. They grow by accreting whatever wanders close enough. But in the 1970s, Stephen Hawking showed something that nobody expected. Black holes are not truly black. Quantum effects near the event horizon cause them to slowly radiate energy, what we now call Hawking radiation. The mechanism involves the behavior of quantum fields in curved spacetime, and the result is that a black hole very slowly loses mass over time. The rate is inversely proportional to the mass. Bigger black holes radiate slowly. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to completely evaporate through Hawking radiation. The supermassive black hole at the center of the Milky Way, about 4 million solar masses, would take something like 10 to the power of 87 years. The largest supermassive black holes we know of, billions of solar masses, would take somewhere around 10 to the power of 100 years. These numbers are so large they essentially cannot be communicated. But eventually, even the last and most massive black hole in the universe will evaporate, getting smaller and smaller, radiating faster and faster as it shrinks, until in a final brief flash of energy, it disappears completely. After that, there is nothing left but an expanding, cooling, empty universe. No structure, no energy gradients, no light, no heat. Just a vast, dark, cold expanse of space, expanding forever. What happens after the last black hole evaporates is one of the most genuinely open questions in physics. We do not know. Some possibilities are straightforwardly bleak. Others are stranger and harder to dismiss, and at least one of them suggests the universe might never truly end at all. The most straightforward long-term fate of the universe is what physicists call the heat death. After all the stars burn out, all the protons potentially decay, and all the black holes evaporate, the universe reaches a state of maximum entropy, maximum disorder, maximum randomness. There are no more energy gradients, no temperature differences large enough to do work, no structure, no information processing. Nothing happens, because nothing can happen. The universe simply exists, expanding forever in a state of featureless equilibrium. This is not a violent end, it is a quiet one, a fade rather than a bang. But there are alternatives. Dark energy, the mysterious force driving the accelerating expansion of the universe, appears constant right now, or at least very nearly so. But we do not know whether it will remain constant forever. If dark energy grows stronger over time, the consequences become dramatically more extreme. At some point, the force driving expansion could become strong enough to overcome not just gravity between galaxies, but gravity within galaxies, then between individual planets and stars, then between molecules, then between atoms themselves. The strong nuclear force that holds atomic nuclei together would eventually fail. In the final moments, the very fabric of matter would be torn apart at every scale simultaneously. Physicists call this scenario the Big Rip. If dark energy instead weakens over time, also possible, then eventually gravity could overcome the expansion. The universe would slow, stop expanding, and begin contracting. Everything would fall back together, getting hotter and denser as it compressed until it reached a state similar to the Big Bang, a big crunch, an end that mirrors the beginning. And then there is the idea that some physicists take seriously, the Big Bounce. Maybe what we call the Big Bang was not a true beginning. Maybe it was a rebound, the moment when a previously contracting universe reached its maximum compression and began expanding again. In this picture, there is no first moment and no last moment. There is just expansion and contraction, over and over, an eternal oscillation with no beginning and no end. Our universe might be one cycle among infinite previous cycles. There is also the multiverse. Some versions of inflation theory predict that the process of inflation, once started, does not stop everywhere at once. In an eternally inflating background, bubbles of universe like ours constantly nucleate, each with slightly different physical constants and laws. In the most of these bubble universes, the constants would not allow atoms or stars or chemistry or life to form. But in the rare fraction where conditions are right, something like what we experience would occur. And in a truly infinite multiverse, any event that is possible happens infinitely many times. We have no experimental evidence that the multiverse is real. We do not know which of these scenarios corresponds to our universe's actual fate. These are possibilities, not predictions. What we do know is this: the universe had a beginning. It has a present full of extraordinary complexity and structure, and it will have a future that is almost incomprehensibly long, mostly dark, mostly quiet, but punctuated by the slow evaporation of black holes over timescales that make the current age of the universe look trivially short. And then, one way or another, things will change. Before we get to the biggest open mysteries, I want to stop and be honest about something personal. Because understanding the scale of all of this, really sitting with it, changed something in how I think about my own life, and I think it might do the same for you. I need to stop for a second and tell you where I actually am with all of this. I spent a long time putting this video together, longer than most things I have made, and at some point, somewhere in the middle of trying to understand dark energy or quantum gravity or the long-term fate of the universe, I had a moment that I was not expecting. I was reading about the degenerate era, the slow, quiet cooling of the last white dwarfs over trillions of years, and something shifted in me. Not in a sad way, exactly, more like a recalibration. I think a lot of people, when they first really absorb the scale of the universe, 13.8 billion years old, 93 billion light years across, hundreds of billions of galaxies, each containing hundreds of billions of stars, feel a certain kind of smallness. Like, what does my life mean against all of that? What does any human life mean? I used to feel that way, and I want to tell you why I stopped. The question of whether a human life matters against the scale of cosmic time is, I think, the wrong question, because it assumes that meaning scales with size, that something is important because it is large or because it lasts a long time. But a piece of music does not become less beautiful because it ends. A conversation is not less real because it is brief. Here is what I actually think when I sit with the scale of the universe now. In 13.8 billion years of cosmic history, for almost all of that time, there was nothing in this universe capable of noticing it. There was matter, there was energy, there were forces and fields and reactions, but there was no one to see it. No one to be curious about it. No one to ask what it is or where it came from or where it is going. And now there is. You are a temporary arrangement of atoms complex enough to look at the universe and wonder about it. That is not nothing. That is the most extraordinary thing in the observable cosmos. The universe noticing itself is not something that was guaranteed to happen. It required specific conditions, specific chemistry, specific evolutionary history, specific accidents, an asteroid at the right time, a mutation in the right place, a billion other contingencies. The improbability of your existence when you actually trace the chain is staggering. None of that makes your existence permanent. None of it protects you from difficulty or loss, But it does, I think, make your existence genuinely remarkable in a way that has nothing to do with how big you are or how long you last. That is where I actually am with all of this, just so you know. Now, to the two biggest mysteries in modern physics, the things that mean that despite everything we know, despite being able to trace the history of the universe from fractions of a second after the Big Bang all the way to the present, we currently understand only about 5% of what is actually out there. The other 95% is a mystery. Here is what we know about what we do not know. Here's a number that should genuinely bother you. The ordinary matter, atoms, protons, neutrons, electrons, the stuff you can see and touch and that makes up every star and planet and person, accounts for about 5% of the total energy content of the universe. 5%. The other 95% is divided between two things we cannot directly observe, cannot identify with certainty, and have been unable to explain despite decades of concentrated effort by the best physicists in the world. About 27% is dark matter. The evidence for dark matter is overwhelming, even though we have never directly detected it. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford were measuring how fast stars orbit around the centers of spiral galaxies. Based on Newtonian gravity and the visible mass of stars and gas, stars at the outer edges of galaxies should orbit more slowly than stars near the center, the same reason Neptune orbits the Sun far more slowly than Mercury. What Rubin and Ford found was that the rotation curves of galaxies are essentially flat. Stars at the outer edges orbit at almost the same speed as stars near the center across a wide range of distances. This was not a small discrepancy. The visible matter in these galaxies could not account for those rotation speeds. There had to be far more mass than the stars and gas you could see, distributed throughout and around the galaxy in a large extended halo. Matter that did not emit light, did not reflect light, interacted with ordinary matter only through gravity. Dark matter. The evidence piles up from multiple independent directions. The way galaxy clusters bend light from objects behind them, gravitational lensing, shows far more mass than the visible galaxies account for. The way galaxies cluster together in the cosmic web matches models only if dark matter exists and has the properties we attribute to it. The pattern of tiny fluctuations in the CMB is consistent with dark matter making up about 27% of the total energy budget. But what is it made of? We genuinely do not know. The leading candidates have been particles called WIMPs, weakly interacting massive particles, hypothetical particles that have mass and therefore gravity, but that interact with ordinary matter only through the weak nuclear force and gravity, making them extraordinarily difficult to detect. Enormous underground detectors filled with liquid xenon or specially prepared silicon, cooled to near absolute zero and shielded from every other source of radiation, have been searching for the extremely rare event of a dark matter particle bouncing off an atomic nucleus. So far, nothing definitive. Other candidates include axions, ultralight hypothetical particles proposed for entirely different reasons in the 1970s, which turn out to also be plausible dark matter candidates. There are sterile neutrinos, versions of neutrinos that interact even less than regular neutrinos. There are primordial black holes that might have formed in the early universe and could account for some fraction of dark matter. We do not know which of these is right. We do not even know with certainty that the answer is one of these. Dark matter might be something nobody has thought of yet. Then there's dark energy, and this is where things get truly strange. In 1998, two independent teams of astronomers were using distant supernovae as distance markers to measure how the expansion of the universe has changed over time. Based on everything we understood, the expansion should be decelerating. Gravity should be pulling everything back, slowing the expansion that started with the Big Bang. What they found instead stopped the entire cosmological community cold. The expansion is not slowing down, it is speeding up. The universe is expanding faster now than it was several billion years ago. Something is causing the expansion to accelerate, something with a kind of repulsive effect on cosmic scales, something that works against gravity. We call it dark energy. But that name is entirely a placeholder. It tells you nothing about what it actually is. It's just a name for the thing driving the acceleration. The simplest explanation is that dark energy is a property of empty space itself, that the vacuum has an intrinsic energy density that does not dilute as space expands. As the universe gets bigger and more volume exists, more of this vacuum energy exists. This would cause the rate of expansion to increase over time, which matches what we observe. Einstein actually introduced something like this into his equations of general relativity in 1917 as what he called the cosmological constant. At the time, he added it to produce a static universe because the prevailing belief was that the universe was not expanding. When Hubble showed the universe is expanding, Einstein called the cosmological constant his greatest blunder. It turns out something like it really does exist, not to keep the universe static, but to drive its accelerating expansion. The problem comes when you try to calculate what the value of the vacuum energy should be using quantum field theory. The calculation gives an answer that is off from the observed value by 120 orders of magnitude. That means the theoretical prediction is wrong by a factor of 1, followed by 120 zeros. This has been called the worst prediction in the history of physics, and nobody has a satisfying explanation for why the discrepancy is so enormous. So the complete picture is this. We live in a universe where 5% is material we understand, 27% is invisible matter we cannot identify, and 68% is some form of energy we cannot explain that is causing everything to fly apart faster and faster. The universe is mostly made of things we don't understand yet. That's not a comfortable place to be scientifically, but it is an honest one. There is one more deep problem I want to address before we close out, because dark matter and dark energy are not the only things we don't understand. There's a problem that sits underneath everything, a problem about the two greatest theories in physics and why they fundamentally cannot be reconciled with each other. And the resolution of that problem, when it comes, will likely require us to completely rethink our most basic ideas about what space, time, and matter actually are. Quantum mechanics and general relativity are the two most successful scientific theories ever developed. Quantum mechanics, and its extension, quantum field theory, describes the behavior of particles and fields at the smallest scales with a precision that has never been matched by any other theory. The magnetic moment of the electron can be calculated from quantum field theory and measured in the lab, and the theoretical prediction matches the measured value to 10 decimal places. That is like predicting the distance from New York to Los Angeles to within the thickness of a human hair. General relativity describes gravity and the large-scale structure of spacetime with equally stunning accuracy. It predicts the bending of light around massive objects, the existence of black holes, the expansion of the universe, the existence of gravitational waves, and every one of these predictions has been confirmed by observation. The problem is that these two theories are fundamentally incompatible with each other. When you try to apply quantum mechanics to gravity, when you try to create a quantum theory of gravity in the same way we have quantum theories of the other three fundamental forces, the math breaks down completely. You get infinities everywhere. Calculations that should give finite physical answers instead give nonsense. This tells us something important. It tells us that our two best descriptions of reality cannot both be correct at the deepest level. There must be a more fundamental theory, one that reduces to general relativity in the large-scale limit and to quantum mechanics in the small-scale limit, but that works correctly in the regimes where both matter simultaneously, like the interior of a black hole, like the first instant of the Big Bang, like anywhere that gravity and quantum effects are both important at the same time. Finding this theory, quantum gravity, is arguably the most important open problem in all of physics. String theory is the most developed candidate. It proposes that the fundamental objects in nature are not point-like particles, but tiny vibrating filaments of energy, strings, at scales far smaller than anything we can currently probe. Different vibrational modes of these strings correspond to different particles. Gravity emerges naturally from one particular vibrational mode, which corresponds to a particle called a graviton. The theory is mathematically consistent in a way that ordinary point-particle quantum gravity is not. String theory also requires extra dimensions of space beyond the three we experience. These extra dimensions are predicted to be curled up at scales far too small to detect with any current or foreseeable technology, which is why we do not notice them in everyday life. The theory lives in either 10 or 11 dimensions depending on the formulation. The major scientific challenge with string theory is that it has not made clear, specific, testable predictions that experiments can check at energy scales we can reach. The energy scales where its effects would be unambiguous are around the Planck scale, about a quadrillion times higher than the energies achieved at the Large Hadron Collider. We do not have the technology to probe those energies, and it is not clear we ever will. Loop quantum gravity takes a different approach. Rather than proposing new fundamental objects, it applies quantum mechanics directly to the geometry of spacetime itself. In loop quantum gravity, space is not a smooth, continuous background. At the smallest scales, the Planck length, about 10 to the power of -35 meters, space has a discrete, granular structure. It is made of finite, indivisible chunks called spin network nodes. Time, similarly, advances in discrete quantum jumps rather than flowing continuously. This resolves some of the mathematical problems of quantum gravity, but the theory has not been experimentally confirmed, and it is not clear that it fully reproduces general relativity in the appropriate large-scale limit. Both theories represent enormous intellectual achievements. Neither has been confirmed experimentally. We are searching for the deeper theory, and we have not found it yet. What we know is that physics is incomplete at its foundations. The two theories that best describe reality cannot both be the full story. The resolution will almost certainly require ideas that go beyond anything in our current toolkit, new mathematics, new conceptual frameworks, new ways of thinking about what space and time and matter fundamentally are. That moment has not come yet, but the history of physics gives us good reason to expect it will. Because every time a deep incompatibility in the existing framework has been recognized, resolving it has led to the next great revolution in understanding. Newtonian mechanics seemed complete until its incompatibility with Maxwell's electromagnetism led to special relativity. Classical physics seemed complete until its failure at small scales led to quantum mechanics. We are standing at what feels like the next such moment. We just can't yet see what is on the other side of it. We are at an extraordinary moment in the history of science. The James Webb Space Telescope is already showing us galaxies from closer to the Big Bang than we have ever seen, and some of what it is finding does not match our models. Galaxies that seem too large, too well-formed, too early. When observations challenge models, that is where science advances. The models will either be refined or replaced. Gravitational wave astronomy is brand new. The first detection happened in 2015. Since then, dozens of events have been recorded. Black hole mergers, neutron star mergers, and signals that do not cleanly fit either category. We are now listening to the universe through gravitational waves as well as light, and every new type of signal opens new physics. Future space-based gravitational wave detectors like LISA will extend our sensitivity to frequencies that ground-based detectors cannot reach, opening up the gravitational wave universe even further. Dark matter experiments are getting more sensitive with each generation. The physics of dark matter detection is a relentless push toward larger detectors, better shielding, more sensitive instruments. If dark matter is a particle that interacts with ordinary matter, even very weakly, improved detectors will eventually find it. The detection of dark matter would be one of the most important discoveries in the history of science. Quantum computing is accelerating faster than most people realize. Useful quantum computers, when they arrive at sufficient scale, may be able to simulate quantum systems, complex molecules, exotic materials, possibly early universe conditions in ways that are completely beyond classical computation. They may reveal new physics not by direct observation, but by enabling theoretical calculations that were previously impossible. Neutrino physics continues to surprise. We now know neutrinos have mass, which the original Standard Model did not predict. The mechanism by which they acquire mass is unknown. Whether neutrinos are their own antiparticles, what physicists call Majorana particles, is unknown. Whether there are additional types of neutrinos beyond the three we know is unknown. These are active research questions with ongoing experimental programs. And somewhere, Probably right now, someone is looking at data that does not quite make sense, an anomaly in a detector, a discrepancy between measurement and prediction, a pattern in the CMB that nobody expected. The history of physics is full of discoveries that came from unexpected directions, from accidents and malfunctions and anomalies that turned out to be signals rather than noise. The next revolution is coming. We do not know which direction it will come from. We will know it when it arrives because it will break something we thought we understood and open a whole new layer of questions deeper than anything we have asked before. That is what revolutions do. Think about what that actually means day to day. Right now, somewhere on Earth, a graduate student is staring at an anomalous data point in a particle physics experiment, wondering if it is noise or signal. A team of astronomers is analyzing a new James Webb image and noticing something that does not match expectations. An engineer is working on the next generation of dark matter detector, pushing sensitivity another factor of 10 beyond what was possible 5 years ago. A theorist is working through math on a new approach to quantum gravity, trying to see if it avoids the infinities that wrecked every previous attempt. This is happening continuously in dozens of countries, at hundreds of institutions, at a scale that would have been unimaginable a century ago. The infrastructure of modern physics, particle accelerators, space telescopes, gravitational wave detectors, underground laboratories, supercomputer clusters, global networks of collaborating researchers, represents a collective investment in understanding reality that has no historical precedent. And consider how much has changed in just the last 30 years. In 1990, we did not know the expansion of the universe is accelerating. We had no direct images of black holes, no gravitational wave detections. We did not know neutrinos have mass. We had not confirmed the Higgs boson. We had not watched neutron stars merge and caught heavy elements being forged in real time. We did not have a telescope capable of imaging the earliest galaxies. All of that happened in roughly 3 decades. The pace of discovery is not slowing down. The questions that remain open are the deepest physics has ever faced. What is dark matter? What is dark energy? How do quantum mechanics and gravity belong to the same universe? What happened at the very beginning? Why is there something rather than nothing? Why do the constants of nature have values that allow atoms, stars, chemistry, and life to exist? These are not small technical details. They are questions about the fundamental nature of reality, and the fact that we have reached the point where we can even ask them precisely enough to search for answers, that itself is a remarkable thing. There is a kind of productive vertigo that comes with really sitting with where physics currently stands. We know so much, and we know so little. We can predict the behavior of particles to 10 decimal places and cannot identify 95% of what the universe is made of. We can trace cosmic history back to fractions of a second after the beginning and cannot say what came before. We can detect changes in distance smaller than a proton and cannot reconcile our 2 best theories of reality. That is not failure. That is science doing exactly what it is supposed to do. Every answer opens new questions. Every solved problem reveals the next, deeper problem. Every theory that works perfectly in its domain points precisely at where it will eventually break down. Quantum mechanics was stranger than classical physicists could have predicted. Relativity was stranger. The Standard Model was stranger still. Whatever comes next, whatever unifies quantum mechanics and gravity, whatever reveals dark matter and dark energy will almost certainly be stranger than anything we can currently imagine. That is what makes right now the best possible time to be paying attention. You are made of atoms forged inside stars. You are the amplified product of quantum fluctuations from the first fraction of a second of existence. You exist because of a 1 in a billion asymmetry in the early universe that we do not fully understand. You are here because of a rock that hit the Earth 66 million years ago, clearing the way for the mammals that would eventually become you. You are the result of an unbroken chain of events stretching back 13.8 billion years, every single link of which had to hold. The universe is almost incomprehensibly large, mostly empty, mostly dark, cold, and for almost all of its history, there was nothing in it that could notice it, wonder about it, or ask where it came from. But right now, In this brief, bright, noisy era of stars, there is something that can. You. And a few billion other arrangements of atoms on one small planet around one ordinary star in one of hundreds of billions of galaxies. That is not insignificant. That is arguably the most remarkable thing in the observable universe. We have 13.8 billion years of story behind us. We have trillions upon trillions of years ahead, most of it dark and quiet. But right now, right here, we get to ask the questions. What came before? What comes after? What are we made of? Why does anything exist? What is dark matter? What is dark energy? How do gravity and quantum mechanics fit together? What happened at the very first moment? We do not have all the answers, but we're getting better questions, and that is how this has always worked. Every theory that works points it where it breaks down. Every answered question opens 3 new ones. Every revolution in understanding reveals a deeper layer of mystery. I want to leave you with one last thing to sit with. The universe does not care whether we understand it. It does not owe us comprehensibility. There is no particular reason the laws of nature should be expressible in mathematics that human brains can grasp. There is no guarantee that reality at its deepest level should make intuitive sense to creatures whose brains evolved to navigate a medium-sized planet at medium speeds. And yet, again and again, it turns out to be comprehensible. Strange, yes. Counterintuitive, absolutely. But comprehensible. The same equations written down on paper actually describe the behavior of particles in accelerators and the orbits of planets and the expansion of the universe. That connection between the mathematics we invent and the physics we discover is itself one of the deepest mysteries. The physicist Eugene Wigner called it the reasonable effectiveness of mathematics in the natural sciences. We still do not know why it works, but it does. The universe assembled itself over 13.8 billion years. It went from a quantum fluctuation to stars, to heavy elements, to chemistry, to life, to consciousness, to telescopes, to particle accelerators, to the ability to look back at its own beginning. And now it is looking forward, trying to see the rest of the picture. The story is not over. It is not even close to over. And the fact that you are here to be curious about it, the fact that the universe arranged itself into a configuration complex enough to wonder about its own origins, is the most extraordinary chapter in the whole story. That is where we are, right in the middle of something enormous, brief, and genuinely astonishing. Subscribe so you do not miss what we cover next.